A warm welcome everyone to this webinar about understanding the performance of a globe valve using multiphysics simulation. Thank you very much for joining us today. My name is Paul Lethbridge and I'm the Director of Product and Solutions Marketing here at SimScale, and I'll be your host today. Today's presenter is Omar Abed. He's an application engineer with SimScale, has a background in simulation and modeling turbo machinery, external aerodynamics, thermal management, HVAC systems, and flow control applications. He holds a Bachelor's of Science degree in Aerospace, Aeronautical, and Astronautical Engineering from Georgia Tech in the USA. Let's take a look at the agenda for today. So we'll be talking for about 30 minutes. We'll start with a brief introduction to multiphysics simulation in SimScale. Then we'll get into the meat of the matter, the live demo of the globe valve simulation. And then we'll wrap up with a 5-minute Q&A and also your next steps to try SimScale for yourselves. Please use the chat panel to say hi, and also feel free to ask questions using the chat panel, or if you can see the drop down, there's a way to submit a question to staff as well. And a reminder that your microphones will remain on mute during the presentation. A quick introduction to the SimScale application. It's basically a platform running on the cloud. It's a multi-physics engineering simulation application, as you can see here. Very broad scope of physics capability. It consists of a GUI, an API, solvers, and the appropriate cloud-based infrastructure at the bottom of that diagram there. And it provides, as you can see in the middle, access to many different types of simulation physics, all based around structural, thermal, and fluid solvers. And this is all accessed within a unified GUI, and the user interface and the workflow is basically the same, regardless of what physics you decide to simulate. So it makes the simulations very intuitive, efficient, and it's all accessed from within your web browser. Now, our live demo today we'll be using just two of those analysis types, internal flow and thermal stress simulation types. So with that, I'll now hand over to Omar.
All right, well, thank you for that, Paul. Hello, everyone, and welcome. I'm really excited to be sharing a live demonstration of the SimScale platform today. So for today, we'll be working with a globe valve model. That's a geometry that we will be working with and simulating around to understand its performance, both for fluid flow analysis, understanding maybe a pressure drop for different flow rates under that globe valve, and as well as just the structural response under high pressure, high temperature conditions. So that's what we'll be going over for today. Quick overview of the different types of analyses. We're going to look at the CAD model that we bring in directly and work through all these different analysis types, whether it's a thermal shock type of analysis, understanding the bolt stress on the structure of the globe valve, and of course the fluid flow CFD analysis. So let me go ahead and switch over to the SimScale platform. So here you can see we're working with the globe valve in the fluid flow type analysis. So here I'm looking at the completed results of the fluid flow. So here you can just see a quick animation of the fluid flow. Of course, you can work with several different types of post-processing tools to understand the flow regime and how it behaves within the valve model. But let me go ahead and take a step back and walk us through how we got to this stage to understand what SimScale is all about and how you'd set up a successful simulation with the platform. So your first step is going to be to bring in your geometry. So your original CAD model is going to look something like this. So this is the globe valve that we're working with. If I go ahead and look inside, you can see the plunger in the globe valve half open. So we're concerned about generating the fluid domain around this. And within our CAD mode, it's a very easy process to generate the flow domain. And when you go ahead and generate that, you'll get the negative space or the actual flow region within the model, as you can see here. So this is what we're going to be using for our flow CFD simulation. So from here, you can go ahead and create a simulation type. Now the subsonic simulation type is one of our proprietary solvers that focuses on, it's very powerful for rotating machinery type applications and flow control. So if you're concerned about accuracy with regards to pressure drops or power requirements for rotating machinery, this is the type of solver that's built for that. But of course, within the SimScale platform, you have access to all these types of simulation types, whether it's basic incompressible flow or heat transfer between solids and fluids, and of course, all the structural types that I'll go over when I move over to the thermal shock analysis type. So I'll go ahead and select the subsonic flow analysis. So from here, when we create a new simulation, you'll see on the left-hand side on the navigation tree, we get the simulation setup show up. And the red circles here are indicating missing inputs for us to define, in this case, the flow problem overall. So the first step is going to be to fill in these red circles and turn them into green check marks by defining the problem. So in this case, I'll go ahead and define the flow material for the flow region. And if you want to go ahead and define your own flow material that's not on the SimScale library, you're able to edit these settings and flow material properties on the fly and change the title to whatever you want it to be. And these will be saved to your account. Now, secondly, we want to set up the boundary conditions, or what are the conditions that the flow regime is operating under. So in this case, I'll go ahead and define it by setting a flow rate coming in and a reference pressure coming out. So if I define a flow rate, I'm actually able to work with just defining a specific flow regime point, and define the face that it's coming in from. But with the subsonic analysis type, we're actually able to parameterize this and define several different flow rates at once. So I can go ahead and create a table in here. In this case, I'll just go with 3 flow rates, or I can go in the browse files section and just bring in a CSV file that has a list of flow rates to bring in. So here I've defined the flow rates coming in. And now I just want to close the problem by defining the reference outlet pressure. So in this case, I'll just go ahead and assign it as a 0 gauge pressure, assuming it's the same as atmospheric pressure outside. Now you'll notice I'm not defining any walls as you would with other simulations, because everything else that isn't defined is assumed to be a no-slip wall. Now under here, under the result controls, we want to, if we want to be able to plot the pressure difference, you're able to just do that by assigning the inlet and outlet faces that you are trying to compare the pressure on. That way, when I go ahead and kick off the simulation, I'm able to look at a plot of each of those flow rates and the pressure difference for each of those flow rates pretty easily. So now we're going to go ahead and kick off the simulation. You'll see that I'm running an experiment. So in this case, because you're working in the browser on the cloud, you're actually able to kick off all these simulations in parallel, and each of these simulations are running on a separate instance. So you're not limited by how many simulations you can run at the same time. It is simply just a matter of what are the different conditions you want to be simulating. Let's go ahead and define those different simulation conditions and run them. So when I go ahead and kick off this experiment, you'll notice I scroll down here, you'll see all these 3 simulations are kicked off at the same time. If I go ahead and look at the completed versions of this same simulation, here you can see the experiment where I tested 3 different flow rates between 0.55 meters cubed per hour and 0.75 meters cubed per hour. So when I look at the result controls, I'm able to look at a plot of the pressure difference that I just described earlier. And here you can see there's the pressure difference for each of the flow rates shown here. So this gives you a quick idea of understanding the, if you're looking at a rotating machinery application, you can understand the pump curve, for example, looking at the pressure difference versus the flow rate. In this valve example, the ideal application is to understand the efficiency of the valve in reducing the pressure or lack thereof. Now I'm going to go overhead and jump over to the actual results again to give you a quick overview of how easy it is to work with the post processor and what kind of results you have access to. So as you can see here, I'm just looking at, again, the particle trace. Here in the particle trace, you can actually modify it to the aesthetic of your liking, so to say. So if you want to show a continuous pumping of the fluid into the flow regime, you can use the comets or the cylinders, as I just showed earlier. Will just give you an idea of where a sampling of fluids coming in from the inlet will travel towards. Next, we have the cutting plane. So in the cutting plane will give you a cross-sectional view that you can modify the location of. In this case, I'm just looking across the middle plane, the mid plane here, but this can be modified pretty easily by looking at the position factor. So here we can see I've moved it closer to the camera. And you can actually pinpoint specific data points around the flow regime by using the inspect point tool shown here to get an idea of what the solution field looks like at a specific point. This can of course be applied for different quantities such as pressure, for example, and velocity. Next, I want to quickly highlight the isovolumes. So maybe I want to understand where high velocity flows are occurring in my flow regime. So the isovolume filter here allows you to color in, so to say, where the flow conditions meet a certain criteria. So in this case, I'm identifying where the velocity magnitude is around 1.2 and higher meters per second in the entire flow regime. And it's colored in with an isovolume to filter out where it meets those conditions in the flow regime. So this is a very powerful tool, our post processor results menu, to give you an idea of what's going on within your simulation, within the results of your simulation. Let me shift gears now over to the thermal shock analysis. So this is a structural analysis that we'll be looking at. So again, here we're starting out at the results really quickly. The conditions I'm undergoing here are a high pressure, high temperature shock flow within the valve to understand how it might respond to thermal shock type behavior that might have an occurrence from a failure in a plant or maybe something, an application where you're flushing out the valve with hot temperature fluid. So here I'm animating the structural response and the stress distributions over a period of time where that shock happens for 2 minutes and then it comes back down to regular operating conditions. So let me go ahead and take a step back and show you how you actually set up this kind of simulation. So again, we start with the original geometry we brought in. So you'll notice here, this is actually an assembly model. There's no issues with supporting assemblies or part files within SimScale. Here you can see the sheer extent of how many parts there are. From here, we're able to create a simulation on this part. So now we're going to move over to the structural simulation types. So there's the static analysis, which is your typical steady load type of condition that you want to be simulating, or dynamic analysis, where there may be objects moving within the space, and this is more for a drop test impact analysis type of simulation. In this case, I'll go ahead and cover the thermomechanical analysis. So this allows you to understand thermal stresses and expansion, as well as those typical steady loads such as pressures and forces overall. So I can go ahead and rename this simulation. Now, you'll notice that all the contacts have been automatically detected. I don't have to manually go ahead and define all the contacts and the mating conditions. If there are mating conditions that are different than where two faces may be sliding between one another, you're actually able to go ahead and select a part that you're interested in. So let me go ahead and select this part, for example, and then right-click, filter contacts by selection, and it'll highlight the filters of the contacts that are contacting this part, and you're able to redefine them. But now I'll go ahead and define the simulation once again. So in this case, I'll go ahead and define the materials of the part. I can go ahead and assign multiple materials for the different parts, the sets of parts, but in this case, I'll just go ahead and define everything to be aluminum. So you'll see here, once again, I'm able to modify both the thermal properties and the mechanical properties of the material and go ahead and rename it, save it as my own material within my account. As for now, I'll just leave it for the defaults. And now we have the boundary conditions. So what are the operating conditions that this system is operating under? As I said before, we're going to be looking at what high temperature and high pressure within the valve, how it would operate under that thermal shock. So first I'll go ahead and assign the pressure condition. So I can assign a static pressure condition if I wanted to. So maybe I wanted to look at what 60 megapascals would look like. Yeah. And I would assign that on all the internal faces. So you can group these faces within the topological entity sets by selecting the faces within the viewport once, and then adding them and grouping them into a entity set so that they're easy to be able to select down the road. So I can assign a static temperature pressure condition, or I can go within the table here and make it time dependent. So maybe I want to look at initially no pressure difference between the inside and outside, and then 10 seconds in we have the shock, and then that shock comes back down after maybe 2 minutes. So 2 minutes later we're back at 0 pressure difference. Now we want to define the temperature loading. So again, here I can define it as a static condition, or I can use the table to make it time dependent. And I'll go ahead and assign it for all the internal faces as well. Now here, our main next operating condition, of course, is to give it a reference point into where the valve is actually fixed. So you can use a fixed support to stop a surface from displacing, or I can use an elastic support to give it some type of stiffness in reference to the outside environment that it's in. So in this case, I'll assume that this glow valve is part of a larger system where the stiffness of this surface is the same as the aluminum that it was assigned to. So in this case, I'll go ahead and do that. And lastly, since this valve is part of a larger system, you can go ahead and simulate the actual convection of the heat leaving the system, right? The heat is not simply just applied in isolation. I can actually go ahead and model that using a convective heat flux. So I can define the heat transfer coefficient and the reference temperature of the outside environment that these outer faces are in contact with, and define the and simulate that heat flux within the model. One last thing I want to actually model in is the bolt preload within the model. So what you're actually able to do is, for all the bolts, as you would in your typical structural analyses, you're not going to hand tight these bolts onto the pipe, especially when it's undergoing high pressures and temperatures. You want to actually preload it with a stress to make sure you ensure it you prevent it from failing and enforce the contact faces to actually stay together with some type of force preloaded in to the assembly. So you can go ahead and define that within here as well. So all of this, all these boundary conditions are modeling several different types of behaviors all at once. So we have the pressure applied internally from the fluid flow. We have the high pressure and high temperature. The elastic support models in some stiffness of displacement of this surface so that we allow it to displace within this larger system that is also displacing. And we have the convective heat flux to allow heat to leave the system, and modeling that by a heat transfer coefficient and a reference temperature of the outside system. And of course, the bolt preloads, so we can understand that pre-stress applied within the system throughout the entire thermal shock process. Lastly, under simulation control, you can go ahead, if you're running a longer simulation, you'd actually be able to modify your runtime. And I did forget to make this time dependent. I apologize. So here is where you'd set up making it a time dependent simulation. So if I go back under simulation control, I'd be able to modify the simulation interval. So how far forward into time do I want to simulate this condition? So in this case, we were concerned about 2 minutes and 10 seconds into the future, what's going on. But yeah, from here, we're able to kick off the simulation. So we'll get an estimation of how long it takes. And we can go ahead and kick it off. So let me go ahead and take a step back into the setup that we just went through. So here was the operating conditions of the flow, of the CFD flow analysis. So we've iterated between several different flow rates in the inlet and a reference pressure in the outlet. For the structural analysis, we've went ahead and simulated the internal pressure from the thermal shock, the internal temperature from that thermal shock loading condition, and the bolt preloads, as well as the heat flux, modeling that convective heat flux leaving the system. So in summary, working with the SimScale platform allows you to look at, we covered how we can look at the fluid flow and simulating that to understand the flow behavior within a globe valve type of application, and understanding how we can look at the pressure drop within the system. We've also looked at the structural response, looking at stress, deformation, and temperature distributions of the valve under the thermal shock conditions. We haven't touched upon the meshing algorithm, but the point is that this is this automated process. So we're able to just adjust the fineness of the meshing algorithm. So I can go ahead and jump over to that again real quickly. So here you can see under the mesh settings, we're simply just modifying a slider. So this automated mesh process allows it so that you're not focused on the nitty-gritty of the simulation, but rather you're just focused on setting up your conditions and understanding okay, your end goal, which is the results of your simulation of your problem. So the meshing process is fairly robust in getting accurate results, and I don't know, well-defined mesh for your problem. But yeah, that's all I had to cover for today. Over to you, Paul. Thank you so much.
Omar, thank you very much. Excellent demo. I hope everyone enjoyed that. As you can see, you can use SimScale to really explore real-world problems. You know, you're not limited in terms of the complexity of the geometry you import, and you're really free to explore numerous different physics effects. So I hope that came across. I think Omar did a really good job covering quite a broad range of capabilities there. So now we have just under 5 minutes left for some Q&A, as promised. We've had a few questions come in on the chat, and what I'll do is I'll select a few, and Omar, and I'll let you, I'll read them out, and I'll let you answer them. So here we go. So it's a good question here regarding discrete particle modeling. Can we use DPM modeling in conjunction to the rotary flow? Or how does particle tracing work? Is it the fluid particle?
Yeah, so that's a great question. Let me start with the second part of the question, and I'll take a step back into discrete particle modeling. So the particle traces that we saw earlier and that you can see on the right-hand side of the current slide up, the particle traces is a visualization tool to look at a sampling of the fluid regime and following the velocity vectors. So it's not necessarily discretizing the flow regime and looking at where a particle would displace under, with a separate specific mass condition or that size of the particle, but rather it's just understanding and visualizing the flow behavior by giving you an animated look of how the flow would interact within that velocity contour in the 3D space. So we currently don't support discrete particle modeling, but rather what you're able to simulate is a passive scalar. So what this allows you to do is, given a concentration of some type of something else within the flow, so this can be an inert gas or a particle that you assume will flow with the flow regime, so something that's nearly massless in the context of the flow density. You're able to visualize how that distributes in your flow domain. This can apply for several different types of applications, whether you're trying to understand how much the air would age in an HVAC type of condition. So understanding it in an internal room type of simulation. And if you're trying to understand, there might be some pollutant coming in within the system, how that flows within the flow domain. So that's what the passive scalar can be used for, to replace that discrete particle modeling feature.
Thanks, Omar. Excellent. All right, a few other questions actually still coming in, so great. Thank you, everybody. So question on, I guess, the calculations down to post-processing calculations. So the question is, it's a bit brief, but I'll just read it as is. Control valve sizing, coefficient of flow, CV calculations. So do we have any of those sort of calculations available?
So can you repeat those three properties once again?
Control valve sizing, coefficient of flow, CV calculations.
So I assume CV is related to flow coefficient. So you're able to use the result control to take out the properties that matter, like the pressure drop, for example, that I highlighted. You'd highlight the two faces, the inlet face and outlet face, that you want to define as your reference for the pressure drop. And you're able to take that out as a CSV file so that you can go ahead and in an Excel or spreadsheet format compute the CV. For control sizing of a control valve, that is the kind of design insights that you can make depending on what is the space of your design study. But SimScale can definitely help or work you through that.
And so I think there's. Go ahead, Kanchan.
Yeah, hello everyone. Just adding to what Omar said, that at the moment, yes, you have to do this in a CSV file, but very soon, possibly in the next few quarters, we'll also have the ability to compute CV or KV values as you might want within SimScale, and this will be part of like a custom result control where you would be able to set up a given sort of a given output using certain input parameters as well as other output already available from the simulation.
Thanks, Kanchan, for stepping in there. Okay, we are getting close on the time here, but I think I'd like to do one more question, which came in. How can I define, or can I define a flow rate as an integral shape? Or another, can I define changeable flow rate with time? I guess there's two questions there. So can I define a flow rate as an integral shape? And the second question is, can I define changeable flow rate with time?
So I assume the first question is related to, understanding that the flow near the walls is going to slow down compared to the flow within the center of a volume. So you aren't able to specifically define that type of contour in the 2D space of the plane that you're defining as your inlet, where your flow rate is coming from. But what is usually tackled within CFD simulations is extending the inlet or extending the outlet where you're defining that flow condition, so that you have time to resolve that contour within the simulation organically, rather than having to define it yourself. So you're able to do that wall modeling internally.
Mm-hmm. All right, Omar, again, thank you very much. So we've had a few other questions. We don't have time to answer all of them, so what we'll do is we will follow up with an email and answer those remaining questions in that mode. So with that, we'll move on to the next steps for you. So we'll move on to the next slide. And yeah, basically, I hope again that you enjoyed the webinar and the demonstration. Hope you had managed to take away some value from this, and now you're hopefully very keen to actually say, well, how can I use SimScale? How can I get into this? How do I try it for myself? And it's relatively straightforward. You just go to simscale.com and sign up. You can also request a one-on-one demo by contacting us directly at sales@simscale.com, and you'll get a response from an application engineer, if you're lucky, from Omar within 24 hours, one business day. And also what we'll do is we will give a recorded version of this webinar. We'll send you a link to that after the webinar. And that will be made available to everybody that registered. So if you wanted to listen again, you'll have a chance to run it through again. Or if you want to spread the good word and share it with some of your colleagues that couldn't make today's webinar, we'd certainly appreciate that. So with that, I want to thank you all again for attending, and this brings us to the end of our webinar. Thank you.